Oh, whoa, what's up, fam squad? Chucky Hats here, and welcome to my TikTok reaction video. Today, I have compiled some of the funniest TikToks on the internet, and we'll be reacting to them, and hopefully, we'll have a couple laughs. So, first one here, we have a little overview of the system. We can see that it starts way up high, and then it goes around on a loop, up a little hill, and then collides with another cart. And then from there, goes down another hill, up, and projectile motions itself onto a board. Now, this is a great, fun little video to watch, and a lot of things work well in it, but there are a lot of places where it could fail. And I'd like to go through those and explain how they could fail and how I mitigated them so this successful run could be made. So, the first mode of failure at the start is if the track has too much friction with the cart will just not go anywhere. And this can kind of happen in two ways. Either the material of the track is going to be way too frictiony for the cart to feasibly move on it, or it won't be a steep enough curve for the car to go anywhere. In this case, it's a little bit of both. So the ways to mitigate that obviously would be to make the coefficient of friction go down, so the force of friction would go down, or as we can see in this diagram, the normal force is what the force of friction depends on. So by decreasing the normal force, we can also decrease the force of friction. To decrease the normal force, we need to consider what that means relative to the force of gravity. Force of gravity pushes straight down on the object, but the object is on an inclined plane. So the purely downwards force is kind of split into two components: the normal component, which can be seen here, and the parallel component, which can be seen here. Now, this will be different based on what the angle of the ramp is. So in this case, theta here is equal to theta here. So we can see that as this theta would get bigger, the force of gravity in the parallel direction would get bigger, while the force of gravity in the normal direction would get smaller. So as cosine of 90 approaches 0, mu times force of gravity times cosine theta, which is going to be this side, is going to approach 0, and therefore the force of friction is going to approach 0, which is good, which means that the track and the cart can start. Now, the next major mode of failure would happen within the loop. As can be seen here, the cart doesn't have enough acceleration to make it all the way around the loop. Instead, it just falls down over here. And again, this can be explained using our formulas. Specifically, the centripetal acceleration that it needs is going to be 9.81 meters per second, because that is what gravity is. So if it's going to fail, it's going to be most likely to fail at the top. So we need to always be more than gravity so it doesn't fall down. And v squared over r is going to be dependent, obviously, on the velocity. So if it's not going fast enough, then it won't be able to go all the way around the loop. Or if the loop is too big, it won't be able to go all the way around the loop. Specifically, to find out how fast we need to go, we can use conservation of energy. So we know that the velocity at the top, using some rearranging of equations, is going to have to be the square root of 2 times the constant of gravity times the initial height minus the height of the loop. And this was found using the formula for potential energy, which is mass times gravity times height, and setting that equal to the formula for kinetic energy, which is 1/2 mass times velocity squared. So plugging this into our equation for centripetal acceleration, the square root goes away when we have v squared. So v squared is going to be 2 times the constant of gravity times the height initial minus the height of the loop over the radius, which in this case is 1/2 the height of the loop, because the height of the loop is just the diameter of the loop. And through some algebraic simplification, we can get that down to just the ratio of the initial height to the height of the loop has to be greater than or equal to 5/4. The next mode of failure is this one. when the cart exits the loop and starts going up the hill, if it goes too fast, it might just fly off the track. And this happens because of kind of the opposite part of circular motion, which can be seen here. If the cart is going upwards at some velocity and the only thing that's pushing it back down onto the track is gravity, if it needs more centripetal acceleration to be pushed towards the center than gravity can provide, then it's going to not be pushed towards the center enough and fly off the track. So to do this, obviously there are two ways to do it. Either you make velocity smaller or you make radius bigger. So that would mean that either the cart has to be going slower or the curve has to be a less steep kind of shift. The next mode of failure happens at the collision. As you can see here, the cart comes up and bumps onto the other cart, and that cart falls off. And the physics behind this is in conservation of momentum. When a collision happens, the momentum between the two objects are conserved, and that includes the direction that the momentum is facing in. So in this case, here's kind of a simplified diagram of it. The cart here is moving not just horizontally, but also somewhat vertically as it goes up the hill. So when it contacts the other cart, as can be seen here, right, it has some vertical momentum, which makes the contact or the collision send the other cart somewhat up and forces it off the track, which is not good. The next mode of failure is, again, at this little bump here after the loop. It could have the opposite problem of being too fast, which is being too slow. And the thing that's kind of interesting with it being too slow is that if we go back to the original video of the successful run, you can see that the initial height that it starts at is higher than the height that it would go up the loop, which means, in theory, conservation of energy tells us that the potential energy at that point is not going to be is going to be less than the initial potential gravitational energy, which means that, in theory, the kinetic energy should not be 0 or less than 0. But as can be seen, that's not impossible to happen, and the reason that it could happen is because of friction. So we need some way to know how much friction there is in the system and how to mitigate that friction in the system. Now, talking about mitigating friction, we've already kind of done in the first one. You either need to make the track steeper, or you need to have a less friction-y material. Now, luckily, this track is made to be not very friction-y, so that is a pretty easy problem to solve for us. But just for the math part of it, for fun, I guess, we can figure out how much friction there is over the course of the system. So we know that the work of friction is going to be equal to the magnitude of the force of friction times the distance along the track times the cosine of 180, because friction is acting in the opposite direction of motion, which means that so then we know that the force of friction is equal to mu times the normal force, and the normal force is the force of gravity times the cosine of theta, which means that at a specific instant, the work of friction is going to be equal to the cosine of 180, which is -1, times mu, which is the coefficient of friction, times force of gravity times cosine of theta, times the distance that it travels in that instant. And because that's an instant, that distance is going to be infinitely small, which we can apply calculus to and just call that small d distance. And now that we have it in this form, we can use integrals to say that, assuming there is a function that gives theta in terms of the distance along the track, over the course of the track, the work of friction will be -9.81 times m, which is the force of gravity, times the coefficient of friction, times the accumulated change of the direction that the cart is going in. and that is done using an integral from 0 to the length of the track. And that will give us the accumulated friction between the start and the point that we're at on the track, which is going to be the L here. The next major mode of failure is it's possible that the track would deform because it's too much force on it. As can be seen here, the track kind of jiggles about and things fall off and the cart really slows down. Is just not a great thing to happen. And the reason that this deforms like that is because it experiences it doesn't experience a centripetal force, but instead it needs to give a centripetal force. To make the cart turn, the track needs to push against the cart at the point where it's trying to turn with the amount of force to make it accelerate at v squared over r, which can be calculated with this. And if the track is not strong enough to support this force, because of Newton's third law, if it needs to push on the cart is going to push back. Then if it can't support it, it's not going to, support it. So the easiest way to fix this is to just make the track stronger. When I made the demonstration video for this, I literally had to take the things out a little bit to make it less strong. So if you just push them in, you'll be fine. And now we get to the final bump here. One potential failure point is that there's not enough speed to get over the bump. And we can find out how much speed it has, again, through conservation of energy. Initially, the cart is going to have some kinetic energy plus some potential gravitational energy. I didn't put that there, but it does exist. And that has to be greater than or equal to the mass times the gravity times the height at the top of the hill. So in this case, I'm talking about the initial height would be here, and the kinetic energy accumulates to here. And then to get over the hill at this point, the kinetic energy would have to be enough to be more than the potential energy up here, so the cart can get over it. But even if it does get over it, that still doesn't solve all of our problems, because it has to reach all the way over to the other side of the board. And to figure out if it can do that, we have to use the projectile motion equations. So we'll have some initial velocity that we can calculate by using conservation of energy, as I just stated. And to projectile motion happens in a 2D space, and the two perpendicular axes, the motion of them can be counted as separate. So we can find the initial velocity in terms of y, or in the y direction, and the initial velocity in the x direction. And with that, we can find time by applying the quadratic equation to the just an inherent projectile motion equation, which is delta p equals v initial times time plus 1/2 acceleration times time squared. If you subtract delta p from both sides, you have 0 equals all that. And you can apply the quadratic equation in this way to get how much time it'll take for the carts to leave the launcher and hit the ground. And then with that, because velocity in the x direction is just constant speed, you can multiply the velocity of x times time to get delta x. And in theory, if delta x is as big as it has to be, which is this large, in that equation, it should be able to clear that gap. So with all of that, we now can see why this works. I applied all of this learning to this track, and by fixing all the problems and making sure that everything worked well, we have a successful run, and it makes it all the way across. Isn't that such a funny TikTok video, guys? Isn't that a silly little... Aren't you guys Chucky hats? Signing out. Goodbye. adios. Good night, everyone. Good night.